Hello, my name is Hadi Zamani from University of California, Riverside. Today I'm going to introduce SAOU, Safe Adaptive Overclocking and Undervolting Framework for Energy Efficient GPU Computing. Modern GPUs with hundreds of computing cores make them well suited for HPC application, especially for numerical computation and vector processing. Matrix multiplication is a heavily used and a key subroutine in many software packages solving problems in linear algebra. Q+MM is a highly optimized CUDA package for matrix multiplication, which will be employed to do the matrix multiplication. But given their high computational capabilities, the GPUs consume a significant portion of the total system power and energy. As technology advances toward deep submicron level, the static power becomes a serious problem. Static and dynamic power can be reduced by lowering the voltage and both voltage and frequency respectively. Our goal is to explore the both undervolting and overclocking to save energy. Vmin and Fmax are the voltage and frequencies that programs runs correctly, but if we go beyond these points, system may experience faults. So we have to correct the potential faults with a low overhead FT technique. Even then, we show that we can save energy. We experimentally measure each program's fault distribution and failure probability when operating beyond Fmax. Silent data corruption, CUDA runtime error, and OS crash are among the notable types of errors that system may experience during overclocking. Since STC errors can be covered through fault-tolerant algorithm, we only focus on STC errors and we do not go for the frequencies which can cause errors other than STCs. Now, according to the results from sensitivity analysis, we develop a realistic fault model to find the failure rate of the applications. The failure rate is obtained using Weibull lifetime reliability model, a well-accepted model for transient and permanent soft errors. Now, how to correct the errors. In case of MM, there are two main techniques, ABFD and checkpoint and recovery. The basic idea of ABFD is to encode input matrices with checksums. Based on the number of faults, we decide on the number of checksum vectors. ABFD is not able to cover errors with more number of faults with complicated fault patterns, so we are designing a low overhead checkpoint and recovery technique. What is checkpoint? Checkpoint is a snapshot of a system state, including stack, heap, global, and register values. Checkpoint and recovery techniques usually relaunch the kernel from the beginning. This is a big problem in long-running kernels. We overcome this by modifying the application code to keep track of the necessary information. Also, we adopt an incremental checkpointing, which preserves only the data that has changed since the last checkpoint. To reduce the performance penalty, all the checkpoint data stored has been moved to the GPU device memory. This avoids the expensive PCI Express bus transfer between CPU and GPU. We evaluated the energy consumption of combined undervolting and overclocking. With combined overclocking and undervolting, we can save about 22% energy in comparison with the original system. Also, performance overhead is only 1.15% of the total execution time. In this paper, we proposed an energy-efficient framework, SAOU, that reduces the energy consumption of GPUs through undervolting and overclocking. Since going beyond the safe frequency or voltage gives rise to faults, we designed an in-kernel, in-memory, an incremental checkpoint and recovery technique to handle these faults. We created an empirical fault model to determine the number of checkpoints at each level of undervolting and overclocking. For a matrix of size 10K in Q+MM, SAOU can save the energy consumption up to 22% through combined undervolting and overclocking without sacrificing the performance. Thank you so much for listening. I would be more than happy to answer any question.